Okay, let's begin. Is my screen share working correctly? I know there is a black thing here, but it shouldn't matter.
Yep, that's fine on our end.
Okay, fine. So let's go ahead. For today, I have something which I think it's quite fun, which is Voyager 1. So I mentioned yesterday that there are a couple of recordings we will be using today. And the first one is a recording of Voyager 1, which was done, I don't remember when it was, 2020 something. So a few years back with the Greenland telescope, which is the largest steerable dish, 100-meter dish. And so it is large enough that we can perfectly see the signal from Voyager 1, even decode the data it transmits. To give you an idea, NASA uses either a 70-meter dish or two 34-meter dishes to receive Voyager 1, and Greenback is larger than those. It is 100 meters, so that works absolutely fine. And we are going to do this as an application of the spectral analysis we did last week. So we are going to compute the spectrum of the recording and see where the Voyager signal is, and also to see how it changes in frequency over time because of the Doppler drift, which is mostly due to the Earth rotation, right? So everything is in this folder. You should have also the file if you click the link. And let me try to see how I want to do this. Yeah, maybe I won't start from scratch. Well, maybe not, because this is actually very similar to what we did last week. So I'm going to comment all the differences, and I'm going to disable most of this and begin like so. So the first thing is about the file itself. We use the file source to play back the file. And for that, we need to know the file format. This one, the file format is complex bytes or complex 8-bit integers. And I basically know that because I prepared the file, doing some data reduction of the file recorded at Greenbank. If you are handed off any random file, you need to know the format, otherwise um, nothing will work. So yeah, for this one, we know that the output type is byte. And I'm setting it to repeat. It will loop forever. It is a 5-minute recording, if I remember correctly. And then we have this purple color, which means bytes. So whatever comes out here is a number, an integer number between minus 127 and minus 128 and plus 127. We want to convert those to complex numbers because that is the most common data type using GNU Radio, and it's the most easy type to deal with for the calculations. So we use this ichar to complex. Ichar means interleaved char, and interleaved means that since this is meant to be complex data, but it is integers, we have I, Q, I, Q, I, Q, etc. So basically the first sample is the I value of the first sample, then the next integer is the Q value of the first sample, and you have I of the first sample, Q of the, sorry, I of the next sample, Q of the next sample. You sort of imagine how it goes. So ichar2complex picks up those pairs of input values and forms a complex number with them. There is this scale factor, which is by how much we divide the input, because complex numbers in GNU Radio, they are usually scaled to be between -1 and +1. For example, you might have observed that your RTL-SDR always gives you numbers between -1 and +1. That's just because of the scaling that it is done in the RTL-SDR source block. And if you had a transmitter, there is also the same convention. If you want to drive the transmitter to its maximum output amplitude, you need to give it +1 or -1. If you give it a number greater than +1 or -1, you are going out of range, basically. So that's the reason we divide by 128 here. And This is done by setting the scale factor to 128. Then there is another technical detail about this recording because of the file format used to record at Greenbank, or because of the way that recordings are done at Greenbank. This output file turns out to be mirrored in frequency. So that means that everything we see on positive frequencies is actually negative frequencies, and vice versa. And there is a very simple way to fix this problem, which is to take the complex conjugate. If we take the complex conjugate of a complex signal, we are mirroring it in frequency. If you remember the Fourier transform properties, this is one of the properties, that the FFT of the conjugate of a signal is just the FFT mirrored in frequency. So this is because of the Greenbank recording format. What else about this file? The sample rate is very close to 3 megasamples per second. So we have almost 3 megahertz of bandwidth. It is a weird number like this because of how they record at Greenbank. There is a much larger sample rate, and then there is a polyphase filter bank which channelizes the whole band into channels of this sample rate. So that is actually the reason. And in here we are using just a single polyphase filter bank channel, which is where the Voyager signal lies. If you are not familiar with polyphase filter banks, that's just a way of chopping up frequency range into smaller and equal pieces. So in the case of Greenbank, I'm saying things from memory, but I think it's, yeah, I don't know, it's a huge sample rate, and then it's chopped up into channels of this size, and however many channels go to the same machine to give you 185 megahertz or something. So that's how it works. Then we have the throttle block, and in the throttle block, we are free to set whatever sample rate we want. This doesn't need to be the sample rate of the original signal. I'm actually using sample rate multiplied by 10. And by doing that, I'm basically playing the file 10 times faster. And I will do that so that we can observe better the Doppler drift by speeding up the replay, basically. If I were to play this back in real time, we would need to be sitting for much longer time until we see the signal drifting in frequency. And then we have this Qt GUI frequency sync, which, as I was mentioning last week, is the easiest block to do a spectrum plot in GNU Radio, but it's not great. And to demonstrate that it's not great, I'm going to run this, and even if I use high averaging, I don't know if anyone can tell me where the Voyager signal is, and it's not this thing. This thing in the middle is just the DC spike. It's exactly in the middle. It's at 0 hertz. And it is because of technical things about how recording in Greenbank works. It's probably a rounding thing rather than anything else. So yeah, in here we have the Voyager signal somewhere, but because this frequency plot is not very good, we cannot see it. And then the whole point of last week was how can we build a better replacement for that block using an FFT, the complex to magnitude squared, an integration. And here I'm integrating for 10 seconds. So this will be important. In order to detect weaker signals, we need to integrate for a longer amount of time. And 10 seconds is good in this case. That's also a reason to speed up the playback, because otherwise I would need to wait for 10 seconds before seeing my first output, and then the output will only refresh every 10 seconds. But in this way, it will keep updating every second, because that's like 10 seconds worth of recording data. And this is the same as last week. So integrate logarithm 10 to get 10 times the logarithm 10. So that's the signal in decibels. And then repeat this just to make sure that this vector sync updates fast enough. And we can run this and compare the two of them. And the difference is very striking. In this one, we can barely see the thing in the middle. Maybe I can zoom in more like this. Whereas in this other plot, the thing in the middle is very, very clear, and we also see some signal in here. And yes, this is the Voyager 1 signal. So we can draw a rectangle like this and zoom in on the signal more. And we observe that it has three distinct parts. It has this thing in the middle, which is very narrow. I will zoom in more later on, but you can see it is very narrow. This is called residual carrier, and it is basically a single tone. And this is what allows the receiver on ground to detect the signal, to log to the signal. As we will see, this is changing in frequency because of the Doppler effect. So this needs to be tracked by the receiver on ground. And then we have these two other signals, which is where the data is sent. That's the reason why they have some bandwidth to them. Any digital signal, the bandwidth it has is usually proportional to the data rate. So these signals, I can zoom in more. They have, I cannot even see it well here because that's a limitation of these radio plots. It only shows me the frequency with two digits, two decimal digits. There where it says minus 0.40 megahertz is always minus 0.40 megahertz. I can look at the x-axis here, and I can see from here to there is 1 kilohertz. So each of these small marks is 200 kilohertz, I believe. And the signal itself should be about 300. Sorry, each of these is 200 hertz. So the signal should be about 300 hertz. That means there is about 300 bits per second. We will dig into that more later on because it depends on whether the signal is encoded and so on. But you can already think 300 bits per second. That's not a lot, but also Voyager 1 is very far. As you know, it's outside the solar system at a very large distance. I cannot even imagine myself. So that's the reason it's only able to transmit a small data rate. Because if we transmitted a larger data rate, we wouldn't be able to decode the information here on Earth. So what else we can see? There are two of these. This also has to do with how the data signal is modulated. I will explain more of that later on. So these two sidebands are identical. They are called data sidebands. And we can also see two spikes. So sometimes there are like two prominent spikes in here, and those actually depend on what data is being transmitted. We will see that when the transmitter is transmitting a long string of zeros, we have these two spikes. So that is interesting. We can see the signal. We can even see it's transmitting some data. Sometimes it is all zeros. Sometimes it is not. What else can we see? If I zoom in to this one, I'm going to place my cursor here, and you can see it slowly shifting down in frequency. And I'm going to leave it there for a while. At some point, the recording will just come back to the beginning, and it will jump in frequency. So now I'm playing the recording again from the beginning, and it has jumped in frequency. So you can see that over the 5 minutes that the recording has lasted, the signal has moved about this much. And if you have seen any of the waterfall plots or spectrogram plots that are used in narrowband SETI searches from Watutil, for example, you are already familiar with this. There is a diagonal line on the spectrum, which means that this narrowband signal is changing in frequency over time. In this case, mostly because of the Earth rotation, but if the transmitter was in orbit on another planet, or if it was on the surface of another planet, it would also be because of the orbit or because of the transmitter planet's rotation. Okay, this was maybe a lot of information to begin with. Any questions, any things I should give more detail to? Okay, the next thing I'm going to do is to use this recording as an excuse to teach you something else, which is that the recording contains 3 megahertz. And that is comparatively a lot of bandwidth because the signal is only here. So it would be good if we can channelize this signal, which basically means if we can crop in frequency and get only this part of the spectrum. So the question is how we can do that in GNU radio. I think I mentioned on the first week that cropping signals of interest in time and also in frequency is quite important in many applications since you actually have recorded more data, but you want to extract what matters to you. Cropping in time is very simple. You just crop the file. It is a time series of IQ values. Cropping in frequency is somewhat more complicated. So this is what we are going to do now. We want to do something so that we only have this part of the spectrum.
I have one question, actually, now
Okay.
that you brought it up. You mentioned that, we have 3 megahertz here. You said earlier that we were taking complex conjugates, that we removed the negative component. Why am I still looking at this graph in negative area? It's between, negative 350 to 400 kilohertz.
Okay. Okay. Yeah. Good question. And let me go back to that and let me actually demonstrate what the complex conjugate does. And that is very easy to do because I can show you how the thing looks like before the complex conjugate and how it looks like after the complex conjugate. Because maybe, sorry, but I need to do this. Yeah, I still can do that, I think. I need to duplicate all of these. I think it will be worth it for you to see it exactly
I
what
didn't want to
happens.
send you down a rabbit hole or take too much
No,
time.
no, 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 no. I think it's worth it because maybe I explain it wrong, and I think a picture is worth 1,000 words. So let me try to come up with a picture. There we go. Okay, this is the picture I wanted to show. So in red, we have the original signal, and the signal is here on plus 300 something kilohertz. In blue is the signal after the complex conjugate. So what the complex conjugate is doing is mirroring in frequency. It's flipping the spectrum over this axis of symmetry. It isn't removing the negative frequencies. It is exchanging positive and negative frequencies.
Well, that's because the channels on GBT run backwards, right?
Yeah, that's because the channels are backwards and the signal would appear here and it's actually supposed to be here. In fact, we can look at.
Why is this of interest? Why are we doing this in the first place?
The complex conjugate.
Yeah.
Well, for example, Doppler drift is of interest. And if you remember the blue signal, which has been corrected to account for this thing they do at Greenbank, drifts down in frequency. This one, because it's a mirror image, drifts up in frequency. And Doppler drift is important. For example, Doppler drift due to the Earth's rotation is always going to drift down in frequency because it's like an S curve, which begins at like on the top and it goes down and it goes like this. So you expect signals, at least the ones who have Doppler drift, mostly due to Earth rotation, to have a negative Doppler drift. And yeah, in this case, basically because of the Greenbank recording format, if we haven't corrected for this, we are getting the wrong measurement.
Okay. I somewhat followed. I'm not completely there yet. I'll have to sit on that thought a little bit.
Yeah, so I hope that makes sense. Another thing which I can point out is this 0 hertz is supposed to correspond to some RF frequency. I don't know if it's on the recording file name. No, it's somewhere. Somewhere on the metadata file you have, there would be a number which is 8.4 something gigahertz. The signal is actually at 8.4 something gigahertz. That will tell you what you are processing here as 0 megahertz is 8.4 something megahertz. But then it makes a whole lot of difference if you say the signal is at 0.38 megahertz plus my 8.4 something gigahertz, or if you say my signal is at minus 0.38 megahertz plus my 8.40 something gigahertz. If someone asks, okay, you've seen a signal, what is the frequency where you have detected that signal? You can imagine you are doing a SETI search and you detect a SETI candidate. Someone wants to observe at the same frequency with a different telescope, and they will ask you, what's the frequency you have detected the signal? And yeah, you need to send them to the right place, which is here.
The blue one is in the correct location, basically.
The blue one is in the correct location. The red
Oh,
one is in the wrong location just because of how the green bank data format works, because of
Oh,
the
okay.
channels are numbered
That makes some
backwards
sense to me.
and mirrored.
That makes some sense to me.
It's just that thing. Without you know, reversing this mirroring, it's like looking to the world through a mirror. And yes, you are seeing everything, but everything is flipped, and you might make wrong measurements based on that. So it's just that thing. But yeah, it was good to explain like this because now you have a very clear picture of what the complex conjugate makes to an IQ signal. It's not the same as the Hilbert transform. Last week I mentioned the Hilbert transform, which removes all the negative frequencies. The complex conjugate flips things in frequency. Okay, so the next thing I want to do is to show you how to channelize. So basically how to select the part of the spectrum where the signal sits. And one reason for channelizing would be to reduce the data rate. Another reason would be if we are going to run any kind of data processing, we might only want to run it over this specific signal and not over the whole bandwidth we have captured. So that's the whole reason for channelizing. And I'm going to try to do this in steps, and because I want to, yeah, I'm going to copy and paste this one again. So I actually want to do the same thing for comparison.
While
So
you're
the
doing
first,
this, I'm sorry, I keep having questions. I don't mean to distract you, but when you say negative frequency, are you talking about actual negative frequencies, like we have some mathematics that somehow outputs that, or are you talking about just negative relative to our focal point, which is wherever we're actually looking at? Negative relative to like less than 8.4, if we're looking at Voyager.
yeah, it's negative relative to the center frequency for this channel. So what happens is the telescope is recording a large amount of spectrum centered somewhere around 8 gigahertz. Then that is channelized into channels of about 3 megahertz of width. Each of the channels has a distinct center frequency. The center frequency for this particular channel would be 8 point, let's pretend it's 8.4 for simplicity. It's going to be somewhat higher than 8.4, but it doesn't matter. So the fact that we see the signal at minus 0.3 really means that the signal is at 8.4 gigahertz minus 0.3
That
megahertz.
makes sense. Thank you.
It's, yeah, everything is relative to the center frequency of this channel. And that is mostly for convenience because if we were, let me disable the second input on this plot. If we were handling absolute frequencies on this plot, for example, everything would be slightly more difficult because everything would be like 8.4 bunch of numbers plus something. And it's actually much better in practice to pick a center frequency and say, I'm going to work with respect to this center frequency. And there are things on the left which have negative frequencies, things on the right which have positive frequencies. Okay. So now the thing we want to do is, because the center frequency is kind of an important reference point to us, and we want to work only with the Voyager 1 signal, we want to move this Voyager 1 signal to the center. We want to move it to somewhere close to 0 hertz. And I'm going to do that first, as I explained last week, which is, sorry. I have my signal here, my input signal. This is the same thing which I'm plotting in blue. And then I'm multiplying it by the conjugate of a complex cosine of frequency. This is a variable I have, which is minus 379.2 kilohertz. This is the minus 0.4 megahertz or minus 0.3 megahertz. I have looked at where exactly in the spectrum is, and that is the number I have entered here. That's 0.3792 megahertz. And we saw last week that by multiplying a signal with the complex conjugate of something which is a cosine, complex cosine, it is shifted in frequency. So we are subtracting minus 379.2 from the frequency of the signal, and so it will arrive very close to 0. And we can see that. We can see that the original signal is here, and now everything has been shifted. So the shifted thing is in red, has been shifted to the right. Now my signal of interest is very close to 0. This DC spike in the center has been put here. You can also see these, they are called the skirts or the edges of the channel. They have also been shifted. So now the boundary of the channel would be here. We have wrapped around. So what happens is this part of the spectrum wraps around and appears here. And this is what we see here. This part is equivalent to this part being pushed to the right, and it appears on the left because the spectrum is actually periodic. You need to think that this end of the spectrum is glued to the other end of the spectrum. Does this frequency translation make sense to all of you?
Mhm.
Okay, great. This is a very common operation. Anytime we have a signal of interest, it is very common to shift it to 0 in frequency. So there are multiple ways to do that, and I'm going to show you a different way, which can be interesting because of simplicity when you are doing things in GNU radio. Also maybe for computational reasons, because this is generating a cosine function, and that might not be the best thing for computational reasons. You might not want to be evaluating trigonometric functions. So there is another block which is called rotator, and I'm just going to show you so that you know it exists and you have multiple different tools to do things. Rotator has a phase increment, so it's going to apply a phase increment to each of the to each of the samples of the signal, and a frequency shift is the same as a phase increment versus time, right? A constant frequency is the same thing as a constant frequency, a constant phase increment over time. Phase is the derivative of frequency. So this block performs a phase increment over time. It applies a frequency shift. And the number we put in here needs to be, this is explained somewhere in the documentation, basically by the formula here. This phase increment is in radians per sample. Every sample, it increments the phase of the output signal by these many radians. So if we want to convert from hertz to radians per sample, the formula is, I have my frequency in hertz. Hertz is cycles per second. I need to convert from cycles to radians, and we know there are 2 pi radians in a cycle. So 2 pi frequency is the frequency in radians per second. And then we want radians per sample. So we divide by the sample rate, which is the number of samples per second. You can think about dimensional analysis and everything makes sense. This is cycles per second. This is radians per sample. This is samples per second. If you write out all of that and you cancel terms, you get radians per sample in the end. And there is
Why
the
is it
minus.
negative?
Sorry?
Sorry. I asked why is there minus?
Yeah, I was going to say that right away. So there is the minus sign because I want to shift in the opposite direction because for simplicity, I've chosen frequency. I've set this to minus 37092, which is where my signal is in the recording. After doing this complex conjugate, we can already forget about the complex conjugate and pretend that the recording was already with the complex conjugate to begin with. So when I look at my signal, I see it on the left part of the spectrum. The frequency is this one. But then I want to shift it right so that it ends up at 0. If I didn't have the minus sign, I would be shifting by frequency, whatever, which is shifting to the left, right? Because frequency is negative. Another way of saying it is the frequency of my signal is approximately this frequency variable. If I want to shift it to 0, I need to subtract the same frequency. So that's the reason I need the minus sign. Just a sign convention. If my explanation is not too convincing, it's also playing the same role of the complex conjugate. So the in here in multiply conjugate. So here I have set my signal source to minus 379, and the multiply conjugate has a complex conjugate in the second input port. This is this input multiplied by the complex conjugate of this input. So the complex conjugate in here is playing the same role as the minus sign in here. Or you can get it right by trial and error. That's also a valid approach. You can do it without the minus sign. In fact, let's do it and see what happens. So this is, well, it's too confusing because by coincidence, it turns out that this falls on top of this. But nevertheless, let me just look at this part. So my original signal is here, and rather than being shifted to the right so that it ends up in the middle, it's being shifted to the left and it ends up here. Yeah, we wanted to shift in the opposite direction. So a minus sign must be missing. That's another way you can figure out this without making mistakes. So hopefully that makes sense. Either way, multiplication with the complex conjugate or using this rotator block, we can get the signal close to 0. Anything clear? Everything clear so far? Okay. Now the next thing we want to do is to filter out. We want to filter out to remove most of the spectrum except this central part where the signal is. And we also want to decimate. Decimate means reducing the sample rate. You know that the frequency span we can represent is equal to the frequency, to the sample rate, because we are dealing with IQ data or complex data. And so because for us, only this part of the spectrum, which is, I don't know, about 100 hertz or even less, is the only part we care about, we should be able to reduce the sample rate. And that means dealing with less samples, so that's smaller file size, less computational load. So everything's good. That's a reason to decimate. So how do we do that? I'm actually going to show it in 2 steps. In the first step, I'm going to set the decimation to 1. I'm going to show you what the low pass filter does and then explain the parameters, because I think it's easier to understand it. Oops, sorry, not this one. If we have a clear picture in mind of what it's supposed to do, and then we can sort of go into how we choose the parameters. So, no. Yes, this is actually supposed to work. So, yeah, you can see how this looks like. I can even zoom out. So the red thing is the signal of Voyager 1 has been moved to the center. And before we also had all of these, but now the filter is basically attenuating by a lot. It's never going to remove completely the signal. Filters are never ideal, but it's attenuating the signal by quite a lot. And so if I look only at this, we only have this part of the signal that remains. So this is what a low pass filter means. It basically means that there is a cutoff frequency somewhere here, and then everything of lower frequency, both negative and positive, passes through the low pass filter, and everything of higher frequency is attenuated. You need to think about it in terms of the absolute value of frequency, or in terms that it is symmetric. So it cuts between this frequency and minus the same frequency, which let's put numbers. What is the cutoff frequency? About 30 kilohertz. So it cuts everything except for between minus 30 kilohertz and plus 30 kilohertz. Does this make sense? Everyone understands what's the goal of this low pass filter? Okay, how do we set the parameters? There is the low pass filter block. It has a gain, which can be used to scale up or down the signaling amplitude, and we do not need to change it. It needs to know about the sample rate. And then the next thing is the cutoff frequency. And since I'm going to use this for decimation, I'm going to choose it with this formula, and I will explain it to you, and hopefully it will make sense. The decimation is by how much we are going to reduce the sample rate. So let me look at what I have, 50. We are going to reduce the sample rate by 50. So basically divide this almost 3 megahertz by 50. And that gives us, let me see where I can put another variable to do the calculation. Decimated sample rate is equal to sample rate divided by decimation. So this is about 58 kilohertz, which is enough to contain the Voyager 1 signal. This is how I chose 50. I was looking for a number which is large, but not large enough that this is too narrow and narrower than the Voyager 1 signal. So, okay, basically this is something slightly wider than the Voyager 1 signal. Then why do I want to set the cutoff frequency at this value, which is 0.5 of the new sample rate after decimation? Well, it makes sense because if the frequency range I can represent after decimation is only between plus half and minus half of this new sample rate, then it makes sense to set the cutoff frequency at this value. Again, going back to the plot here, the new frequency range will be between plus and minus 29 kilohertz. So plus and minus 29 is somewhere over here. So it makes sense to place my cutoff here because in any case, my new sample rate can only represent things here. If I had some signals here, they will alias. And for example, something here will appear somewhere around here. It's like the thing we have observed with the frequency shift, where the edges of the spectrum shifted, like from the right edge to here. It's the same thing. Once we decimate, if we have a signal here, then it will appear here. If we have something here which is not filtered out, it will appear here. So basically, my new channel is going to be this width. I need to remove everything which is outside, or it will appear in unexpected places in here. So that's the reason I use this cutoff frequency, and you can always use this formula, or you can use this formula quite frequently. It's half of the sample rate divided by decimation, or half of the new sample rate. Transition width or transition bandwidth, it's sometimes called. What is that? So you can see, if I zoom in closely, this filter does not go immediately from the pass band, which is this part, to the stop band, which is this part. It has a transition. And how large this transition region is depends on the number of filter coefficients. If we have few filter coefficients, then this transition will be very large, which is bad because, I mean, an ideal filter decays immediately. and that is mathematically impossible. But in general, we want to have this thing decay as quickly as possible. So a larger number of filter coefficients will give us a steeper transition region or narrower transition region. Basically, the trade-off here is about computational complexity. If we have more filter coefficients, that is more computational complexity, because an FIR filter works by multiplying the samples by all the coefficients and then summing up. So it's more calculations the CPU needs to do. If we have fewer coefficients, then it's less computation, but the filter is not as good. So there is always a trade-off. A good ballpark value is 0.1 times the new sample rate, which means that this part of the spectrum, which is like these edges are because of the same. The channelizer that was used at Green Bank Telescope also has an FIR filter, which has this transition because it cannot be perfect. It can have a certain number of coefficients, probably not very many, since it runs on an FPGA, I think. And here we can afford more coefficients running with less sample rate on the computer, etc., etc. So 10%. This region where we have the transition is 10% of the whole output range. We have basically 5% in here and another 5% in there. That's how it works. You can set this number to other values like, I don't know, 25% or 5% or those are all good choices, and depending on which one you choose, you will get higher or lower CPU usage. Any questions so far? Okay, the next thing that remains is to apply the decimation. And I had decimation variable, so decimation 50. And now I need to delete all of these because this is a problem you might run into when you are trying to feed in to the same block, to one of these display blocks, for example, signals of different data rates. That will not work properly in GNU Radio because GNU Radio requires that the data rate in all the inputs of the same block is the same. To explain why, the main reason is that it is going to plot something from the first input and something from the second input at the same time, and then it's going to fetch another thing from the first input, another thing from the second input, and plot them at the same time. If the second input is delivering data at a different rate, then we run into a problem because data is arriving faster to one of the two inputs. In this case, it will be the first one because we are not applying decimation. So data will queue up and the flow graph will freeze. So I'm not going to do that. I'm going to use a separate Qt GUI vector sync, which is basically the thing I have here. And there are a few changes. I will explain them in a second. But first, I want to show you what decimation looks like. So this is the original input signal. This is the signal after decimation. We can see that now the frequency range is only the about 58 kilohertz or so that we have selected. This is the transition of the new filter. That is the same thing we were seeing. And by decimating, we have basically reduced the data rate, and the spectrum we have is only now between plus 29 and minus 29 kilohertz. And so we only have the Voyager 1 signal here. Does it make sense? Okay, what changes between this FFT, etc., and this second FFT? You can see that the FFT size changes. In here I have 262 something something. And why is this weird number? Well, because it is a power of 2. It is often better for the CPU when FFT sizes are a power of 2. So in this case, I have chosen it to 2 to the power 18. That's a reasonably large number. And the reason for that is to get good SNR. And last week we saw that when we have narrowband signals, it is good to have a large FFT because then the frequency resolution increases, and so we get less noise per FFT bin. So that's, I think I mentioned that last week, and if not, I mention it now. The effect of the FFT size on the spectrogram for narrowband signals, when we increase the frequency resolution, then the noise power per bin decreases, but the signal of interest is still just concentrated or one or a few FFT bins. So we increase the signal to noise ratio. We increase the chances of being able to see the signal. So that's the reason why I have set it to 2 to the power 18. But now I'm decimating by 50, so the sample rate is less. To achieve the same frequency resolution, I should use a smaller FFT size. So to have exactly the same resolution, I would need to divide this value, 2 to the power 18 by 50, but that is not a power of 2. I'm dividing by 64, which is a power of 2, to give me another power of 2. And the power of 2 is 2 to the power 13. It is the same as 2 to the power 18 divided by 64. So yes, I need a different FFT size in these two because they use different sample rates. So to have similar frequency resolution, I need to account for that. The FFT size depends on the sample rate and the frequency resolution. And then how am I doing that? I have a variable NFFT, which is used in all of these blocks to set the vector size. And then I have NFFT2, which is used in all of these other blocks to set the vector size and the FFT size. What else? The number of FFTs I'm averaging, I'm also computing that separately because the numbers are going to be slightly different. I have here the original sample rate, the large FFT, and 10 seconds. That gives me that I need to sum up 112 FFTs to plot a spectrum. On the other one, it's a similar number because this thing is supposed to be very similar to sample rate divided by NFFT, which is what we had in the number of integrations. But because this NFFT was divided by 64, not by 50, which is the decimation, I get a slightly different number, 72, rather than 112. So yeah, on the second one, I'm also doing almost 10-second integrations by summing up 72 of these in the integrate block. What else is different? Maybe I should also explain this, how to get correct frequency measurements on the x-axis. So we need to set the starting value. And in this case, it's minus the sample rate divided by 2 and divided by the decimation. And I want to show the result in megahertz for convenience. So I multiply by 10 to the power minus 6 because this is in hertz. This is the most negative frequency I have, minus 1/2 of the sample rate. It's after decimation. You need to remember we have decimated, so the new sample rate is sample rate divided by decimation. And then what is the step value? So that it's how many hertz or megahertz really we have per FFT bin. So that's the sample rate divided by the FFT size. I have this decimation because it is meant to be the new sample rate. So sample rate divided by decimation. And then this to convert from hertz to megahertz. And in this way, I can get my plot. And I have also something similar for the other one. I see this one has the label frequency megahertz. This one doesn't because I forgot to put it. Where do I put it? Here. Here we can enter frequency megahertz. Here we can type in PSD, which means power spectral density in decibels, and we can also put units here, megahertz, and dBs for the y-axis. And so we have megahertz, and the cursor also says megahertz and dBs. This is also megahertz and dBs, and the same one for this. Okay, any questions? Right. What else do I have about this channelization thing? The other thing I have is that since shifting in frequency either with this rotator or with the multiply, conjugate, and signal source cosine is a very common operation, there is a block which does all of that. So in most cases, this is the block you should be using. It is called frequency exlating, and exlating means translating. It's an abbreviation for translating FIR filter. And this performs the frequency shift and the low pass filter as a single operation. And it's also slightly more CPU efficient in this way. But for us, the main reason to use it is that it is more convenient to have a single block which does the combined work of two blocks. How does this work? This works in combination with one of these low pass filter tabs blocks, because the tabs need to be defined in a variable. So I will get to how to do that in a second. The other things we need to set are the decimation. This is the same as in low pass filter. The center frequency. This is the frequency where our signal is. So now we do not need to care about the minus sign or those things. This block internally handles the minus sign to shift the frequency in the right direction so that it ends up in the center. And then the input sample rate. This is the input sample rate. The output sample rate is sample rate divided by decimation. So tabs. The tabs are a list of numbers, and you can even see them if we mouse over. It's a complex vector length, about 1200 numbers, and we can see a few of them there. How do we calculate these low pass tabs? There is this low pass filter tabs block, which is just like the low pass filter. It has the same parameters except for the decimation, but it's used to set a variable, and we set the name of the variable here, low pass tabs, or you can give it any name you want. And then we can set the same name here. So that's how these two blocks are linked by this ID, which is set in here. And the rest, I have just copied the same formulas I had in there. So half of sample rate divided by decimation, and 0.1 multiplied by sample divided by decimation. And we can try this just to see that it does exactly the same thing as the other approaches. So yeah, it does. It's working as it should. Any questions? Okay. That is the end of this flow graph. We will be moving on to a short break in a minute. Before I'm going to say what we are going to do after the break. First, I wanted to show you at some point during these tutorials, like a real world use case of gnuradio doing something more complicated, because in the tutorials we are putting together these examples, which are mostly educational, but it's also good for you to see gnuradio working on a more complicated problem that someone might actually use in production somewhere. So what I'm going to show you is how to decode the data in this Voyager 1 signal using gnuradio. I'm not going to explain all the details of how to do that, but I'm going to show you the flow graph working and show you how it's structured, so that you have a basic understanding about digital communications. And that is another reason why we have taken the effort to go through how to channelize, etc., because we will be using that in this data decoder. And that should be pretty quickly. The rest of the second part of today is going to be using the RTL-SDR stick for FM reception. So we have seen how to receive FM radio stations in GQRX, and listen to the music. I want to show you how to do the same thing in GNU radio, and that also uses the frequency translating FIR filter because we will be receiving about 3 megahertz of bandwidth, which is what the RTL-SDR gives us. There will be several FM radio stations in that bandwidth, and we want to select and extract just one of them. So we will do that with the frequency translating FIR filter. I think I'm screen sharing again. Yeah. So what I have here is the flow graph for decoding the digital data that Voyager 1 transmits. And I'm going to give you a quick rundown of how this is structured without going into all the details of how it works so that you have an understanding of how a digital communications receiver for this particular type of spacecraft communications work. And this also has a certain interest beyond digital communications because there are, I would say, philosophical questions about whether our understanding of communications, like RF communications, has any universality to it, or whether there are things which we are doing as humans in a certain way that another intelligent species might do in a different way. And that is completely relevant when we are trying to search for technosignatures, because we can wonder, do extraterrestrial communication signals look like our own? Do they not? And there are many things which are probably not the same, but there are other things which might be a common ground. For example, binary code. People wonder whether that's like a mathematical universal construct, and you always come to binary code. So in digital signal processing, there's always the concept of frequency. It's important you always come back to it. But anyhow, it's good to have some notion of digital communications if you are looking for extraterrestrial communications. Anyhow, we have the recording file source, the same thing as before, frequency translating FIR filter. This is exactly the same we had before the break. I have slightly adjusted this more accurately because I need the center frequency of the signal slightly more accurately than I had in the previous flow graph. And then what are the steps to decode the digital data on this signal? If you remember, the signal had two different parts. There was a narrowband signal in the middle, which I said this is the residual carrier. And then there were the data sidebands carrying the data on the sides. This PLL is used to track in frequency and phase the residual carrier. The whole point of having the residual carrier in there, in the middle of the signal, is so that the receiver can use this, which is a mathematical operation known as a PLL, a phase-locked loop, to track the phase and frequency of the signal. So that is how it locks onto the incoming signal, and we will see how that looks like. Then the next thing we are doing is extracting the data sidebands. We saw that they are on the two sides of the residual carrier, and they are a certain distance from it. The distance is known as the sub-carrier frequency, and we will have a look at it on the spectrum. But I already can tell you it is about 22.5 kilohertz. That is the reason I have my center frequency about 22.5 kilohertz. That is, again, doing the same thing as before, shifting one of these data sidebands to the center so that we can process it further. There is a small detail. Why do I have a real part, imaginary part? This will become clearer when we look at this plot. So I'm not going to explain it by now. So now after this filter, we are looking at just the data sideband. And the next thing we need to do is the data sideband uses something which is known as phase modulation. It encodes binary by the phase of the signal. Let's say phase 0 means 1, phase 180 degrees means 0. So basically by shifting in phase between 0 and 180 degrees, it accomplishes transmitting digital data. That's one of the multiple ways we know about modulating digital data on a radio frequency wave. And to receive that, we need to integrate the energy which is within each of the bits in the signal. We need to collect all the energy. And that is what this filter is doing. It's adding all the samples which correspond to one of the bits in the signal. So it's adding samples together to accumulate the energy. And then there is this symbol synchronization because the receiver doesn't know ahead of time where the boundaries between those bits happen in the signal. There needs to be an algorithm that detects when these boundaries are. And this is done more or less by edge detection. So when the signal changes from 0 to 1 or from 1 to 0, there is like a jump in phase. And this symbol synchronization algorithm is able to see that there is a jump, and so that needs to be a bandwidth. That needs to be a boundary between symbols. So that's symbol synchronization. Once we do that, we have complex valued numbers for each bit that was transmitted. Whereas before we had basically a sample rate and we had a digital stream of samples, now we have one sample per symbol or one sample per bit. The samples are still complex, and there is a residual frequency error because this frequency might not be perfectly exact, for example, because of Doppler. So we have this Costas loop, which is correcting the additional frequency error on the signal. And finally, we can extract the values of the bits, which are still going to be floating point numbers because the signal has noise. So if there were no noise, the signal would be either +1 or -1 exactly at this point. But because there is noise, it will be +1 plus some noise, -1 plus some noise. And sometimes the noise is large enough that it can flip a -1 to a plus, something negative to something positive, or vice versa. That is known a bit error. So because of noise, there can be bit errors in the transmission. And there's a reason why we keep the floating point numbers, because they also encode the amplitude of the data. So if I give you something like 0.1, you could say, well, that looks like a 1, but I'm not really sure if it was a 0, so a -1 that was flipped over because of noise. If I give you 1.5, you can say, yeah, I'm definitely sure this is a 1, and the 0.5 is noise. So that's the whole point. You have like a probability associated to each of those that you receive. You have a probability that the bit you received is 0, probability that it is 1. That's the reason of keeping floating point numbers here. And then because there are bit errors, there are mathematical algorithms that work to correct those bit errors. They work by sending additional redundant information, and by using that redundant information to remove the bit errors. The simplest error coding that you can think of is sending the same thing 3 times. If you send the same thing 3 times, then if one of those is corrupted, still 2 of them are going to be correct, and you just look at what is the majority. So if the 3 are the same, then you know there are no errors, and it is fine. If one of them is different, you know which is in error, and you're able to say, yes, 2 of them say 1, 1 says 0, so it's meant to be a 1. This is very inefficient because it triples the data size, and there are much more efficient but more complicated mathematical methods of encoding redundancy on the data and being able to correct for bit errors in this way. So the whole rest of it is for error correction. And a few other things I will explain when I reach the point. Let's run it. On the throttle, I also have this 10 times faster than real time. So let's run it so we can see some plots. So this is the output spectrum after the PLL. This is the thing that logs to the residual carrier. And what we can see is that the residual carrier is in blue, that is in the in phase part or real part of the signal. And the data modulation, you can, if I zoom in, you can see it's red. So the thing on blue is just noise. So that is the reason that we have this PLL, because we want to have the data in the quadrature part and the residual carrier in the in-phase part. And by looking at it with this PLL is how we achieve the this thing to be in the quadrature part. This has stopped because the recording has reached the end and I don't have it set to repeat. Yeah, was there a question?
No, I just need.
Okay.
Sorry about that.
No worries. What else? I mentioned, I'm going to put it again. There is, so on the imaginary part, on the quadrature part, which is where we get the data modulation, we extract with a frequency translation FIR filter one of the sidebands. They are actually the same since the signal is real at this point. And this is what the data subcarrier looks like. So this is this. We have just decimated to a few kilohertz. And then we are doing the symbol synchronization. Where was that? Symbol synchronization, Costas loop to correct for the any additional frequency offset we might have. And we are plotting what is known as the constellation of the signal. Each of these dots represents one complex number for one bit in the transmitted signal. And the ones which are positive real part are meant to be a 1. The ones which are on the left half, so negative real part, are meant to be a 0. So you can see this is a bunch of 1s transmitted, binary data. This is a bunch of 0s. Some of them are close to the middle, and maybe some of them have flipped over. These would be the bit errors. So that's why we have error correction coding. That's the remaining part of the flow graph. And this is showing a few things about error correction coding. So there's something called Viterbi decoder. It does one of the error correction algorithms. And for example, let me show you the output of one of the two of them. There are two of them because it needs to be aligned with the signal with pairs of bits. And because we do not know a priori how to align ourselves, it's a good way to do is to try both hypotheses in parallel, and one of them will work. But for what I'm explaining, just looking at one of them is good enough. So basically we can see the signal changing between 1 and -1 or 1 and 0 a bunch of times. And then there's a long string of +1s. This is meant to represent a long string of zeros in the signal. So something else I should mention is this could be the original signal, or it could be the original signal completely flipped because of how the receiver works, because of how this Costas loop works. This might be flipped, and maybe these are the zeros, maybe these are the ones. So there is something else, which is a synchronization word. Let me show you the plot. At the beginning of each data frame, there is a specific sequence of bits that tells the receiver, hey, this is the beginning of a data frame. And we can do a correlation to try to find that sequence. And whenever there is a peak in the correlation, that means the sequence has appeared. So here is a correlation peak. That means here is the beginning of a frame. There is a second correlation peak because of how Voyager transmits the data. It is playing it back from a tape recorder. It is a very old spacecraft, so it doesn't have a hard drive or something like that. It has a tape recorder. And there is also a synchronization word in the tape recorded data. So that's the reason there is two of them. But basically, you can see it like here. There's the first, the beginning of a data frame, which goes up to here, another data frame. So by computing this correlation, with the synchronization word, and by looking at where the peaks appear, the receiver can say, hey, this is a frame, this is another frame, and so on. And each of these frames contains binary data. And we can look at one of them, for example, this one. So the beginning, this is the synchronization sequence. If you look at all the frames, you can see it's the same in all of them. And you can see it somewhere later on. I forgot what it was here. This is where it appears the second time because of the tape recorder. Where is it? No, I don't. Okay, here, C03915 ED3. And a whole bunch of data, which I don't know how it is formatted because there is not much public information about this, and it is a very old spacecraft, so people have even forgotten. The engineers who did this have retired or even passed away, so very few people understand how the whole system works. And you can see some data, some zeros, etc., etc. And all of these working with Ground Radio and the green band recording. And you can also see these RS errors is the number of bit errors that, or byte errors that were corrected by the Reed-Solomon recorder, which is one of the algorithms. So now you have, on the one hand, I think this is pretty cool that with anyone's computer, you can go run this thing and have some green bank data turned into actual telemetry data that was recorded on the tape of the spacecraft and then later on transmitted. So that's pretty cool. And also now you have a rough understanding of how any digital communication system works. The specific steps will be different in depending, I don't know, if it's a cell phone, if it's Wi-Fi, or if it's something else. But the concepts are transferable. They are similar concepts in all kinds of digital communications receivers. Any questions about this? Okay, FM broadcast is the next thing I have. And for the FM broadcast, I have the RTL-SDR. I have it again plugged to the USB with an antenna. If you have an RTL-SDR and want to run this now, you can. There is the RTL-SDR source. If for whatever reason you don't have an RTL-SDR and want to run this, there is a file source on the flow graph. This is the FM broadcast flow graph, which is also on the GitHub. This I did last year. Let me go back to the GitHub. So there is this short recording, FM broadcast, something, 2024, June 15. So that's when I did last year, the FM broadcast thingy. And there was a recording. File source, it is very straightforward. So you pick the path for your file using this file chooser. If you download it to a different path, which will probably be the case, you need to choose the file here. And then this particular file is complex data type so that it's easier for you to use. So you can enable this block and disable this one if you are going to use the file source, the recording. But I'm going to work with real-time signals from the radio because that's the whole point of having a radio here. So RTL-SDR source, we covered that the first week, how it works, frequency sync to see our signals. And we are going to tune to one of the stations, which is at 98.8 megahertz. So I'm tuning to 98.5 megahertz. And then the RTL-SDR, and then I'm tuning to the signal, which is at 300 kilohertz above that center frequency. So that's how I tune to the station I want. Basically, I have this RF frequency, 98.5, and I have this tune frequency, which is 300. That will give me a total of 98.8. Which is a nice classical music station here. The same thing as before. I want to decimate to something which is reasonable for FM, We will see what's the bandwidth of your typical FM signal. And then I have that on the low pass filter tabs, and the rest of the flow graph, I'm going to disable it because I will explain it step by step. But for now, we have things that we already know how they work. Let me show you all of this. So this is the RF spectrum, as it says. I don't know if I ever mentioned it, but you can set a name on most of these plots. So RF spectrum here at 300. So the center frequency, just to recap, is 98.5 megahertz. We could show it here if we wanted. By the way, in case you ever want to do that, you can set the center frequency to any value you want, so 98.5, and this will display accordingly. But I find it easier to work in relative frequencies relative to the center. So we know our station of interest is at 300 kilohertz. So it's the one here. And there is another station here, another one, maybe another one. And the reason for extracting this single station is we want to remove the power from all the other stations so that they don't interfere with the receiver. So we do that by the same as before, low pass filter tabs, frequency translating, FIR filter. How wide is one of these signals? So it is about, I don't know, 300 kilohertz bandwidth should be plenty. You can see from here. So that's what I have here. Something like this. So this is the output of the decimation. I'm decimating by how much? 10. You can sort of choose these values often by trying. So you choose 10, for example. If that looks too narrow or too wide, you change it to 15 or 5 or whatever. You can also calculate. So anyhow, this is our FM signal. Any questions about this so far? Okay, this should be all quite familiar to you. So this is, I've been saying this is an FM signal. What does FM mean? FM means frequency modulation. So it means that the audio signal, in this case, either music or a presenter speaking, is an analog signal. It is a voltage that is changing over time. And to encode that on the radio frequency signal, we change the frequency of the radio signal. So if our audio signal at any given moment is a positive value, we increase the frequency of the transmitted radio frequency signal slightly. If our audio frequency is a negative value, we decrease the frequency of the transmitted RF signal. And because an audio signal is changing constantly between positive and negative values, we saw that on the first tutorial where I did the audio demo with the microphone, for example. The signal is always moving between higher frequencies and lower frequencies. So that's the reason why in the spectrum it looks like this. It's actually like constantly changing, like sweeping this thing as the audio is modulating it. But when we compute the spectrum, it averages over the FFT duration, so we see this shape. I'm explaining all of this to motivate that if we want to get the audio on the FM signal, the thing we need to do is to measure the frequency of the signal, because that's where the audio is encoded. And to measure the instantaneous frequency of the signal, there is a GNU radio block which does it, and that is called quadrature demode. That stands for quadrature demodulation. It's like a historical term of how this used to be done in analog receivers. The main thing you need to know about this block is the formula here, which is somewhat complicated because it's written in LaTeX. If I tell you the formula in words, maybe it's easier. It computes the phase difference between a sample and the previous one. And that's the instantaneous frequency, basically, because instantaneous frequency, it's what's the change in phase over time. So the change in phase over time of one sample is the instantaneous frequency on that sample. It's like taking a derivative by subtracting two neighboring values when you use discrete time sampling. So the units of this thing are, well, the units of the output are radians per sample. There is a gain which gets multiplied by these radians per sample. You could set the gain to 1 if you wanted, but I'm setting this to a nicer value. So when you have a frequency modulated signal, there is something known as deviation, which in the case of FM is 75 kilohertz. And that's how much we shift the signal when the input has a maximum value. So I was saying when the audio is positive, the signal is shifted to a higher frequency. When the audio is positive and it has the maximum value, the frequency is shifted plus 75 kilohertz. That's what the 75 kilohertz deviation means. And this formula, the only thing it does is that it will give you 1. So when you have a frequency shift of 75 kilohertz, it scales things to give you +1. That's the whole point. But you could also put 1 here and you would get an audio which is not scaled between +1 and -1. Doesn't matter so much. So something we can do is to look at the spectrum of this thing to see if it makes any sense. I'm going to set 1 input. And we can also look at it in the time domain, but we will do that later on. So this is what we have. This is the spectrum after quadrature demodulator. This is the spectrum of the frequency of the signal. And we get some things we might have expected and some things we might have not. All of this is noise, so I can zoom into this part of the plot, which is the interesting one. And here we can see some power. We can see that it is changing also with the modulation of the signal. So this is audio. It's changing as the audio contents of the radio station are changing. And it makes a lot of sense because it goes from about 0 hertz. So the human hearing range begins at 200 hertz or so, or even less. I would say maybe 50 hertz. So even less than 50 hertz, whatever, a couple tens of hertz. So it begins almost at 0 and then it goes up to about 15 kilohertz, which is almost more or less where the human hearing range ends. So this is all like audible frequency range. Then the question is, what's the rest of the thing? Does anyone have any ideas?
Are they like harmonics, maybe?
Well, it could be, but if there were harmonics of something, they would have the same shape or a similar shape, and they really don't. You maybe could say that maybe this one is a harmonic of this one, because at the moment they look similar, but you can see this one is changing, and this one is always the same shape, more or less. So yeah, the answer is no, but it was a good suggestion. Any other ideas or guesses? Well, I'm going to tell you. So FM radio stations are usually stereo. They transmit stereo sound, like left and right audio channels. That sounds nicer to play music. But in here, we just have a single audio signal. So then the question is, how do they transmit stereo? Stereo is two separate independent audio channels. And that's what this whole thing is doing. This one is the stereo signal. And I will get back to explain how exactly stereo works and why it's done in this way. This one, you can see it's never changing. It's tone 19 kilohertz exactly. It's just a signal of constant frequency. It's known as a pilot tone. It is used to generate frequency reference that we will need to make use of this stereo signal. So if you look at the stereo signal, it seems symmetric. It's always like symmetric, and it seems the middle is 38 kilohertz. That's correct. That's twice as this, and that's no coincidence. There are harmonics in play here. So the harmonic of this thing is meant to be the center of this. And so this pilot is transmitted so that we can find where the center of this thing actually is. Because the receiver might not be exactly at the appropriate frequency, or the transmitter might have a small frequency error or something. So even if you know that on paper this is supposed to be centered 38 kilohertz, you actually need to transmit a reference to find out. And then finally, if you have an FM receiver, maybe on a car or one of the radios that has a display, it will tell you the name of the radio station. It sometimes tells you the name of the program or the piece of music they are playing. So where is that? And that is here. This is a digital signal. It is called RDS, which means radio data service, I think, which is transmitting those things, the name of the radio station, the current program, and other basic information. This is similar to the Voyager 1 signal. It's I know it sounds like a joke that a spacecraft which is way far out is transmitting a digital signal which is similar to an FM radio station that might be a few blocks away, but that's the thing. They are, both of them are low data rate digital signals. So we are going to ignore this one for today. Just you can know that it exists. We will do some of the stereo processing, time allowing, but for the time being, I want to do the mono part of the signal, which is just this one. So you have an old receiver that only receives mono, or if you have an FM station which is only mono, you will only have this one. And to play back the audio of this thing by sending it to the computer speakers, we need to remove all of these. So we already know how to do that. We can use a low pass filter. The cutoff frequency can be, I don't know, 16 kilohertz more or less. So let me see what I have here. I can enable it. 17 kilohertz I have set. So 17 kilohertz in here. It needs to be before the 19 kilohertz tone, so it's not very critical. Anywhere in here is fine. That is to remove all of this, and that is why I had a second channel in here. So let me put it back, and I think, yeah, the config is maintained. So I have after the low pass, and I can connect it and apply the change. So nothing mysterious. After the low pass, we only have this, and the rest is very attenuated. So that's good, because we do not want to have a 19 kilohertz tone coming out of our speakers. What else we need to do? So something about the sample rate. The sample rate of this signal here is 320 kilohertz, or 320 kilo samples per second. A computer sound card cannot use that sample rate because it's meant to play back audio signals which have lower frequency range. So we need to convert the sample rate. And for that, there is a rational resample block. So I'm going to explain sound cards usually have, let me enable all of these. They usually have a few sample rates they support. I already mentioned these on the first tutorial, and 48 kilohertz is a common sample rate many sound cards support. So we are going to use 48 kilohertz. How do we convert from 320 kilohertz to 48 kilohertz? We can do that with this rational resampler block. We say it needs to decimate by 320, it needs to interpolate by 48, and the net effect is multiplying the sample rate by 48 divided by 320. So that is how we get from 320 kilohertz here to 48 kilohertz there. That's just what this is. Whenever you need to do one of these frequency changes, and the frequency change is not an integer decimation, as we have done here, for example, that we decimate by 10, you can use this rational resampler block, and it will also handle low pass filtering for you. So that's the way we get an audio signal, which is the mono signal here, at 48 kilohertz. I'm also sending it to the speakers. I think I'm sharing the speakers over the Zoom call, so you will be able to listen. But at the moment, I have this multiply constant block. This is connected to audio gain, which is an QTQ entry, so the same thing as always. I want to enable this by putting something like 0.1, and we can listen to some music. So I guess this comes across. Let me disable it again. So yeah, some cello music playing, which is what we can see here. And you can see the signal has been scaled by this deviation so that the maximum, which only happens sometimes, is +1 and -1. Questions at this point? Okay, this is basically what GQRX is doing when we use the GUI to tune to an FM radio station, and we tell it it's wideband FM and play it back. It's doing something very similar to this to extract the audio frequency signal from the FM signal. So the next thing I want to show you is how stereo works. More because I think that it's fun, just to give you creative ideas about how to encode data in signals, than because I think it's particularly relevant for astronomy. But anyhow, so what we need to do is there was this 19 kilohertz pilot carrier, this thing here. So we need to extract this frequency, and we are going to log to that frequency using, again, something known as a PLL. I really don't have the time to explain in all detail how it works, but you can think about some kind of machine which is looking for something that looks like a tone of 19 kilohertz or very similar on the input, and it's going to search for it, log to it when it finds it, and then it will produce a clean tone of the same frequency and phase. So if this were to have a small frequency error, let's say it's maybe 19 kilohertz plus 0.1 hertz, because some frequency error somewhere, the output of my PLL will be a clean cosine function of this 19 kilohertz plus 0.1 hertz. So it's basically a way of cleaning up this pilot tone because there's all this noise. So what am I doing here? I have the FM demodulated signal. It is real signal. I haven't mentioned explicitly, but all of this part of the flow graph is real because after quadrature demode has measured the frequency of the signal, and the frequency of the signal cannot be a complex number. It's a real number. It can be positive, it can be negative, but it's a real number. There is no imaginary frequency. That's a weird thing. Well, it makes sense if you do a Laplace transform, but we're not going to do any of those. So no imaginary frequencies. Frequency is real. This PLL, it only works with a complex signal. There could be a version for real signals, but there isn't. So there's a very simple thing we can do, which is convert the real signal back to a complex signal by putting zeros on the imaginary part. You can remember that this null source generates zeros. And then we have this PLL. It is basically looking for a signal between 19 kilohertz minus some small number, which I think is 5 hertz or something like that, and 19 kilohertz plus this 5 hertz margin, and it has a bandwidth, which is a technical thing that says how fast this thing can detect the input signal, how tolerant to noise it is, etc., etc. So without getting into too much details, this thing is looking at the 19 kilohertz tone and producing a very clean 19 kilohertz tone, which doesn't have any of the rest of the noise or other signals. But that is a 19 kilohertz tone, and we want a 38 kilohertz tone because what I want to do is that the stereo signal is this thing, the middle is this thing. It is a real signal that has been shifted in frequency to 38 kilohertz. So we want to shift it back in frequency to 0 hertz using this 19 kilohertz pilot tone multiplied by 2. So to multiply the frequency of something by 2, we can square that signal. We can multiply the signal by itself, which is the thing I'm doing here with this multiply block. Why is that? If you think the output of this is a complex exponential, it's a complex cosine. It's like the signal source we were using to generate a clean tone. So it looks like exponential of 2 pi times the frequency times time. If I raise that to the power 2, because of the properties of the exponential, the power 2 goes to the exponent, and now I have exponential 2 pi times the frequency times time times the number 2. But that times the number 2, I can group it with frequency, and I can have times twice the frequency. So basically, squaring a signal, raising a signal to the power 2, multiplies the frequency by 2, because this this exponent 2 goes on the exponent, which is where the frequency of the signal is. So that's the way to remember. In this way, we generate a 38 kilohertz tone, which is derived from the pilot tone. That's very important. It cannot be any 38 kilohertz tone. And then what else? We also convert our signal here. I don't know why I have a second float to complex, since this is exactly the same thing twice, but anyhow, doesn't matter. So again, I'm converting the original signal to complex again. I'm doing a multiply conjugate, so 38 kilohertz tone here. It will shift the frequency of the signal to the left by 38 kilohertz, and that is what we want to do. We want to move that stereo thing from plus 38 kilohertz down to 0. So that's the reason we have multiply conjugate. As you see, often in signal processing, the same concepts come up again and again, a frequency translation. So I need to generate something to generate that translation, and there's going to be a multiply conjugate. So it's always similar operations for many different things. And then I want to look at the real and imaginary parts by separate. Let's leave it as that for now. And let's look at how that looks like. So this is the stereo subcarrier spectrum. It is, well, at the moment there is a match. So what happens with this radio station, sorry, that's also an interesting thing to see, that when there is the presenter speaking, there is very little stereo content. It's always on the mono signal. When there is music, there is more stereo content. Now you see it is probably music. So all this thing here has been shifted so that the middle is now on 0. So this 0 is the middle of this thing. Let me maybe zoom in more. And you can see, for example, this clear peak is this peak here. Maybe you can see that most of the power is on the red part. And that's because of how the signal for the FM radio station is defined exactly on paper. This is supposed to be a sine wave. There is supposed to be a sine wave here rather than cosine. So that is the reason we get everything on the quadrature. In the phase component, there is supposed to be noise and errors. Like you can see, this is not perfectly flat and not perfectly symmetric. So that is why we get non-zero in phase. Question?
It was just needed. Someone else needs.
Okay. So what I mean by the whole of this is that the signal we want, the audio signal we want, is this red thing. It's on the quadrature or the imaginary part. So we are going to take this imaginary part and do something with it. And then what else? I haven't really explained how the stereo system works because something about stereo is you need two independent signals, left and right. And we have two independent signals, this one and this one. But I have said that this one is the mono signal. So mono is not the same as left and it's not the same as right. So the way that this works for backwards compatibility, and also because some stations do not have stereo at all, is that this signal is left plus right. That's what we mean by mono. If we have a single speaker, then what should we do with it? If we want to play a stereo signal, let's play the sum of left and right. That totally makes sense. So this is left plus right. And then this thing is left minus right. That's what we mean by the stereo signal. It's the difference that we should apply between the left and right channels. And of course, if we have mono, which is left plus right, and we have the stereo content, which is left minus right, we can recover left by adding. So left plus right plus left minus right gives us twice left, which is nearly the same as left. And then subtracting, so left plus right minus left minus right gives us 2 times right, which is right. So that's what we get the left and right speaker signals. And since we are 5 minutes from the end, I'm going to go through that sort of quickly. We still want to have the same low pass filter cutting at 17 kilohertz for the stereo signal because it's supposed to be an audio signal as well. And the rational resampler, so this is the same thing we had before for the mono signal. We are applying it to the stereo signal. And now I know it is with this zoom level, maybe I do one less. Still, it is complicated to see. So anyhow, you bear with me. I'm adding the mono signal comes in here, the stereo signal comes in there. So I'm adding them to get the left channel. So when I have an audio sync with two channels, this is the left and this is the right. And then I'm subtracting the mono, which comes here from the top, minus the stereo signal to get the right channel. And then I'm also plotting all the audio signals. So we have the mono signal, we have the stereo signal, we have left and we have right. And we can see how that looks like. So you can see in blue, it is the same thing as here. So it's the mono audio signal. In red, you can see the left minus right. So depending on what's been played, it will have very little content. Sometimes there is not much difference between left and right. And sometimes there will be more content on this red stereo signal. And then you can see left and right. So they are close because there are common signals on left and right, but you can see that sometimes they are slightly different. Maybe I'll try to stop in here, for example. So you can see for some of the parts of the wave, they are very similar because this is very close to zero. For some other parts, for example, this region, this is more different from zero, and we have, what is it, green. So the green speaker and the black is the right speaker. So left is green, black is red. And that's how we encode two signals. I'm going to try to play, let me see, I need to disable this one. I'm going to play the stereo sound. I think there will probably be no difference for you. It depends on the sound system you have. I told Zoom to share stereo sound, but who knows?
Las 2 últimas horas llega ya el turno, llega Germán
It's
García
a person
y la
speaking.
Taberna del Puerto. Hasta mañana. Adiós.
So, yeah, sorry, that was a person speaking. So when there is a person speaking, because there is a single microphone, or more or less a single microphone, you can see the stereo signal is almost close to 0. Now there's some piano music or something, so you can see there is more stereo, or I don't know what is going on. I will turn up the volume right now in a second. But you can see, depending on what it's been played back, you can see differences in left and right, and sometimes I can hear it since I'm using headphones. With your sound setup, it might not be easy to hear it. Anyhow, let's play it back for a few seconds.
Es un verdadero placer daros la bienvenida a este nuevo espacio que hemos preparado para acompañarlo en este.
So I don't know, some background piano music and some presenter speaking, and occasionally some stereo content. So that's all I had for today. Any